So next thing we would like to look at is how do we go about decreasing the speed of the molecules, of the atoms of the molecules which we interrogate. And if we decrease the speed of the molecules, that corresponds to a lower temperature. So this is all often called cooling, different ways of cooling our sample. Now we have already seen that by tuning the laser, we can talk to only some speed groups of some atoms or molecules which are moving with a certain speed. And we can use this, if we use photons like small balls which we throw at the molecules or atoms, we can slow them down by the recoil of the photons. So let us have a quick look at this. So here we have in 2 steps the process of firstly having a photon coming in and hitting a molecule. And when this photon is absorbed by a molecule, it is transferring a momentum to the molecule. So that means it gets a little kick in this direction. And then at a later time, the atom or molecule emits a photon in a random direction. And this time it gets a little bit kick in this direction. So if it emits it in this direction, it gets a little bit of a kick. So the total transfer in this kind of process, if we have a photon coming in from here, it gets a little bit of a kick in this direction, it's going out, and it gets a kick in this direction. So the total transfer is in this direction here. Now, if we are always absorbing photons from this direction, that means that the kicks are always this kick is always in this direction, and the emission kick is randomly in any direction around, so that to the first degree will average out. So that means that by having light coming in from this and hitting it, we can hit the molecules in this direction here. So now the trick will be to try and hit only those atoms which is moving towards us, because if they are moving towards the laser beam, that means if we constantly keep hitting them from this direction, we will slow them down. Yeah, here is just again showing that if we have many occasions, the average emission is 0, and we will get a momentum kick in this direction. Sorry, in this case the laser is coming from this direction, so we will get a kick in this direction over here. So here we have an energy diagram of an atom. So in this case we say that the energy difference between the ground state and the excited state is the distance between these lines when the atom is standing still. And if we now send in a laser beam which has a little bit too little energy to interacting with this, these two won't be interacting together. But if the atom is moving towards the laser, that means that the light will be Doppler shifted and it will appear to have a higher energy. And now all of a sudden it has enough energy to interact with the atom. So that means that by doing it like this, we will only interact with an atom group which is moving towards the laser. So if we now have a setup, we have a sodium oven over here, and then this emits atoms with different speeds in all direction, and then we have a small aperture, and that selects only the atoms which are moving in this direction. So that means that to first order, we don't have very large movement in any other direction, and then we take a laser beam from this direction here, over from this direction, and we start off by having it much detuned, considerably smaller than the energy the atom needs to be excited. And that means that we will catch all the atoms which are moving really quickly. And then if we slowly scan the laser closer and closer to this transition, that means that we will be catching atoms which are moving slower and slower, and keep on slowing them down until we get close to them, and then they will be moving very slowly. So this is the idea of tuning the laser. But we could also, if there is some way of tune the distance between the excited state and the ground state, we could also tune the energy difference of the atoms while keeping the laser at the same energy all the time. And the next thing we're going to look at is a setup to do this. So what we have here is a magnetic field coil where we can do it such that we can Zeeman shift by applying a magnetic field. We can Zeeman shift the energy levels. So that means, and by having a stronger field in this direction and then having a coil which gives a smaller and smaller field as we go along this coil, that means that we will get a big shift in this direction, and then we can have a smaller and smaller shift as we go along. And that means that over here we will be catching the atoms which are moving really fast, and then they will be slowed down, and as they go down they will go slower, and then we will catch they will go slower. And now the atoms which move slowly, they won't in this direction, nothing will happen until we get to the point where the distance is correct to be catching them. And that means that when we will be exiting this setup here, all of the atoms will have been caught up and all of them will be moving really slowly. And here we have a picture of such a setup. So you can see how it's got more winding in this direction, and then as we go along the beam there's fewer and fewer windings. So we have a varying magnetic field along the length of this tube. Now we can not only cool them in one direction as we looked on so far, but you can actually do it in several directions. So if you have, if you set it up like this, that you have light beams which comes, one light beam comes in this direction, one comes in this direction, one in this direction, one in this direction, and so on. That means that they will be cooled in all degrees of freedom, and the atoms inside here will be caught in what normally is referred to as like an optical molasses. So inside here the atoms will be cooled down. So if you in this case scan all the beams from, just like we did in the first discussion, scan the beams from far away in energy and closer to the middle, then you will catch a whole bunch of atoms here in the middle, but there is no preference where within this overlap region you catch them. So you might catch them here, you might catch them here. So it's not really pushing them to the middle. Okay, so how can we solve this? I mean, in the one with a varying magnetic field, we could stop them at the end of this tube because we catch them at different places depending on how fast they are moving. Now there's a way of doing this in 3 dimensions as well. And that's something called the Magneto-optical trap, or MOT. So in this case you make 2 changes. Firstly, you add 2 magnets like this, where the current in them are counter-propagating. So I mean, this coil down here has a magnetic field going up, and this has a coil magnetic field going up, and that creates, in the center, creates a quadrupole magnetic field. And again, by Zeeman shift, that will shift the atom levels of the atoms as you move towards the center of this. So that's one change. And this gives you energy level diagram as a function of how close you are to the center, as the one we see here over here. You see that we have these coming in like this for the different MF levels. The other change you do is that you use circular polarized light. So that means that you have light coming in, and then you over here it goes through a lambda quarter plate and it's turned into circular polarized. It goes down, hit the mirror, comes back, and is circular polarized in another direction. So from the light beam coming from this direction has a sigma plus beam, and the light beam from this direction have a sigma minus, has a sigma minus polarization. So circular polarized in different direction. And this is the same for all the beams coming from all the different direction. And that means that the different beams talk to different MF levels here. And since these ones are scaled, just like in the first one we saw, that means that if you're far away, you will catch the atoms which are moving fast, and then as you move closer and closer, you will catch the atoms which are moving close. So if you have an atom moving fast away like this, it will be caught far away, and then it will be slowed down. So that means that its speed will slow down, and if the slower speed, that means they will be moving randomly in some direction, and eventually it will be caught in the middle of this of the MOT. So the atoms moving around, the atoms moving away from the center of this MOT, as they get further away, if they have high speed, they are more and more likely to get a kick back to the center as they come into resonance with a ready tuned laser. And with a trap like this, you can cool down the atoms to about 1 microkelvin. If we again makes our example, of iodine, and we have cooled them down to 1 microkelvin. That means that we have a speed of about 1 centimeter per second. And if we have a 1 millimeter beam, that means that we have as the same as we had last time, that means that we have an interaction time of 0.1 second, and that means that the line width we can measure, the smallest line width we can measure, is about 10 hertz. So that means that we have gone from about 100 kilohertz to 10 hertz, so that's another factor of 10 to the power of 4 improvement. So why can't we get them to a lower temperature than in this case 1 microkelvin? Well, that is called something which is the recoil limit. So when the speed, if we have an atom standing still, or if an atom is moving with a speed corresponding to the kick of a single photon, that means that we cannot kick them with less than 1 photon. We can't kick them with half a photon, and that means that with this technique we cannot give them a smaller nudge than with a single photon. And that is called the recoil limit. So if we want to go beyond this limit, then you first cool them with a MOT, and then you transfer them to a purely magnetic trap, where there are no lasers. Such a trap is formed by having an inhomogeneous magnetic field, and they are trapped with a magnetic force due to their magnetic moment. Now this force is much smaller than the recoil force which we had in a MOT, so it's not strong enough to keep the atoms trapped. So now we have atoms moving with different speeds, so they have different energy. And the atoms which are moving the highest speed we would like to get rid of. Because if we get rid of the fastest atoms, that means that the atoms which are left are moving slower. And this is called evaporative cooling. And in principle, what you do is that you lower the trapping potential, say something more about exactly how you do this, and so that it's not strong enough to trap the atoms which are moving fastest, and you're left with only the slow moving atoms. So here we have our magnetic trap, and only the atoms which is in the spin state m equal to 1 are trapped in this magnetical trap. So this is the trap potential here. So if we are in this spin state over here, they are anti-trapped. And what we do now is we take an RF frequency and we drive the atoms, the fastest moving atoms, from MF equal to -1 to MF equal to 1, and then we get into this anti-trapping state. And once we get into the anti-trapping state, that means that they just leave the sample. So if, for example, down here we take and remove all the atoms which moves faster than this, that means that we have left with the atoms down here in the trap. And after a little while they will be redistributing, and we will have a new distribution of atoms. Once they have equalized, we have a new distribution of atoms moving slow. To quickly recap, we have a varying magnetic field compared to where we are in the vicinity of this on this cloud, so that we have a varying magnetic field according to this, and that means that our MF levels are split according to this. And when we take and apply a radio field, we move the atoms from the non-trapped state from the trapped state into the non-trapped state. And if we now scan our radio frequency in, we'll be left with only the atoms which move slowly. So, is there any other way of trapping ions or atoms than the one I described here? And yes, there are several. But I will describe one which we use in the research group which I work in. And that's simply to take and consider a solid material as a natural trap for ions. And normally the line widths for atoms in solids are very wide, but under some certain circumstances they can actually be very narrow. And so these crystals, they are crystalline material, and in them there is doped in some rare earth ions with a low concentration. And these rare earth ions, they are naturally very well shielded to their surrounding. And then these materials are cooled down to a few Kelvin, And at these low temperatures, you get very narrow line widths. So even though this is a solid state material, you get line widths in the order of kilohertz. And furthermore, since it's a solid state material, that also means that you have a very high atom density. There's lots of atoms in a solid material. So you typically have about 10 to the 19 rare earth ions by cube centimeter. And this also means that you can get a very strong absorption, which is not so easy to do in things like in other kinds of traps. So you can, for a typical one of these, you can have an absorption of about 20 per centimeters, and there are materials which have absorption up to 15,000 per centimeter. But again, all of this is at liquid helium temperature, that is at about 2 Kelvin. And again, if you would like to know more on this, please come and ask me when we have these questioning hours, and I would be more than happy to discuss this in much more detail. So we have now talked about that we can do this very precise spectroscopy with very high accuracy. But we also need to be able to refer this in some way so that we can measure the wavelength of our absorption lines. So that means that we need a very precise ruler to measure where in wavelength we are.